Chen and fellow students. My name is James, student ID R13921031. Today I'm presenting my final project proposal for this class. The topic is on security vulnerabilities in multi-modal RAG systems, specifically focusing on adversarial attacks on vision language document retrieval. This project addresses a critical emerging threat at the intersection of retrieval-augmented generation and vision language model. Let me start with the core message of this proposal. RAG systems introduce novel attack surfaces through their retrieval mechanism, enabling adversaries to poison knowledge bases, extract private data, and manipulate model outputs without compromising the underlying large language model. What makes this particularly concerning is that attackers don't need to hack the LLM itself. Instead, they exploit the visual document retrieval pipeline, which has received for less security scrutiny than text-based systems. This is the critical gap my project aims to address. So why do we need multimodal RAG in the first place? So traditional text-only RAG systems struggle with complex real-world documents. Think about a medical report with X-ray images or a financial statement with embedded charts and tables. These documents contain critical information in their visual structure that pure text extraction simply cannot capture. This is where Visual Language Model VLM come in. ColPali, released in 2024, represents the state-of-the-art approach. It processes PDFs as images end-to-end without needing traditional OCR pipelines. This preserves all the visual information, layouts, charts, formatting, even font styles that might be semantically meaningful. Enterprise adoption is accelerating rapidly. Healthcare systems use these for radiology reports. Like financial institutions analyze like 10K VLMs. The legal firms search through contracts. So these stakes are incredibly high. So we are talking about systems making decisions based on medical diagnosis, financial data, and legal agreements. So, but here is the problem. The diagram shows the multimodal RAG architecture. Notice the attack surface I have highlighted in red. When PDF or images enter the system, they go through a VLM encoder to create embeddings, which are stored in a vector database. An attacker who can inject malicious documents into this knowledge base or manipulate the visual structure of the document can compromise the entire system without ever touching the LLM itself. So, this is fundamentally different from text-based attacks, and existing defenses are not designed for it. So this brings us to the specific research question I am addressing. How vulnerable are RAG systems to adversarial attacks, and what defenses can effectively mitigate these threats? So I have identified 4 key attack factors that are unique to multimodal RAG systems. First, poisoning attacks and adversarial inject malicious documents with adversarial visual content into the knowledge database. Because the retriever processes images holistically, subtle manipulations in layout, embedded text, or even how to say this, patterns can cause these poison documents to be retrieved for specific queries. Second, privacy leakage. The extraction of sensitive data from the retrieval database. If an attacker can craft queries that cause the system to retrieve and expose private documents, or if membership inference attacks can determine whether specific confidential documents exist in the knowledge space. This poses severe privacy risk for enterprises. Third, prompt injection via a retrieved context. This is particularly insidious. Malicious instructions can be embedded directly into document images, hidden in layout, encoded in visual patterns, or disguised as legitimate and fed legitimate context. Sorry. When these documents are retrieved and fed into the generator VLM, the hidden instructions are executed. Fourth, membership inference. Can an attacker determine if a specific or proprietary document exists in your RAG knowledge base just by observing the system's behavior? This violates data confidentiality even without extracting the actual content. So now here's the critical gap in the literature. Most existing work focuses either on LLM security or on standalone vision language model attack (VLM) attacks. So very few papers have studied how these vulnerability manifests so specifically in RAG systems, where there's an additional retrieval stage where my project will be one of the first systematic studies, hope so, of multimodal RAG security. So before diving into my approach, let me position this work in the context of recent research. I will cover three categories of attack that inform my project. So first is the a visual prompt injection attacks. The most striking example is from Klansman and its colleagues, published in Nature Communication just this February. They tested four state-of-the-art VLM, Cloud 3, GPT-4o, and Reka Core with sorry with 594 different attacks on medical imaging data. The results: all models were susceptible. They embedded sub-visual prompts, instruction hidden in ways that human observers couldn't easily detect, directly into medical images like X-rays or CT scans. These prompts caused the models to provide harmful or incorrect medical advice. Kimura's works showed similar vulnerabilities with Go hijacking attack, achieving a 15 almost 16% attack success rate on GPT-4v through visual injection alone. Second, cross-modality jailbreak attacks. This is where it gets really interesting. The LLM multimodal attack, modal attack, which will be published. So sorry, it's the MML attack, which will be published at SEL 2025. Uses an encryption decryption strategy. ACL has passed, so it's not will be has been published. Sorry, has been published at ACL 2025. Uses encryption decryption strategy inspired by cryptography. They encrypt harmful instructions in images using transformations or word replacement, then use text prompts to guide the VLM to decrypt and execute these instructions. Their results are stunning. 98% attack success rate on GPT-4o using SafeBench and 99% on MN SafeBench. They use something called evil alignment, where they frame the attack as part of a video game production scenario, which bypasses safety guardrails. So these ICLR work showed compositional attacks that pair adversarial images with benign-looking text prompts. The triple AI paper by Qi demonstrated universal adversarial images that can jailbreak aligned VLNs across different prompts. Third, we would like to uh, this is very crucial for my experimental design. So, automated jailbreak generation, the idea paper introduces something revolutionary, using VLMs themselves as red team models to generate multimodal jailbreaking prompts. They achieved 94% attack success rate on mini GPT-4, and importantly, these attacks transfer to other models with 82 to 88% success rate. They have released VL Breakbench, a dataset with 3,654 adversarial samples, which I will be using in my experiment. So the key insight from all these prior work is that VLM have fundamental vulnerability in how they process and align visual and textual information. And this is critical as none of these papers study RAG systems specifically. So now let's look at the study of the art in multimodal RAG technology and what defenses exist. So ColPali from in 2024 represents a major breakthrough in visual document retrieval instead of the traditional point painful pipeline OCR layout detection chunking strategies. ColPali processes document images directly using polygamma vision language model VLM with a late interaction mechanism similar to CalBERT. It achieves a state-of-the-art performance on the Vital Ray benchmark. So the beauty of ColPali is that it preserves everything: visual layout, tables, charts, even fonts. This is perfect for enterprise use cases. And here's the security concern I'm highlighting. There has been zero adversarial robustness evaluation of ColPali. Nobody has tested, maybe somebody has, but I haven't surveyed it. What happens when you feed it adversarially crafted documents? So on the defense side, the most relevant work is Hidden Detect, which has been published, published in ACL 2025 alongside the MML attack paper. So Jim and propose monitoring the hidden states, the internal activations of VLMs to detect jailbreak attacks. Their key insight is that VLM exhibit distinct activation patterns when processing unsafe prompts versus safe ones. It's tune-free, meaning you don't need to retrain the model, and it surpasses state-of-the-art detection methods. But, and this is the critical gap, hidden detect was only evaluated on standalone VLMs, answering direct queries. It has never been tested on RAG systems where there's a retrieval stage, where documents are fetched from a knowledge base and where the generation happens in a different context. So here are the specific gaps my project addresses. So uh, one, no security evaluation of visual RAG system exists, and the second, all these VLN attacks and defenses are studied in isolation, not in the RAG context. And third, we don't know if attacks like NML or IDEATA can poison ColPali retrieval. And fourth, we don't know if hidden detect can defend. Sorry for the out of range. I will modify the slide later. And fourth, we don't know if hidden detect can defend RAG systems during the generation phase when retrieval adversarial documents are in the context. So my project hopefully it can be the first systematic security analysis that brings all these pieces together. So let me describe my approach. So I am proposing a comprehensive three-pronged framework that to systematically evaluate and defend multimodal RAG systems. So first, threat modeling for multimodal RAG. I need to clearly define the attacker's capabilities and goals in a specific context. Can they inject document into the knowledge base? Can they manipulate query inputs? Or what are they trying to achieve? Poisoning retrieval, extracting private data, or executing jailbreak attacks? I will develop a threat how to say taxonomy. Uh, taxonomy. Is this correct? Sorry. Pronunciation. Right, taxonomy. Sorry. Just want to make sure that's the word. So, um, where am I? The first point, private. Yeah, taxonomy, right? So I will develop a threat taxonomy specifically for visual retrieval systems, extending work from text-only RAG security. So second, novel attack development. I'm adapting three state-of-the-art VLMs attacks for RAG context. The first is visual corpus poisoning, inspired by MML's encryption-decryption approach. Instead of attacking a standalone VLM, I will inject documents with encrypted malicious context into ColPali's knowledge base and test if they can be retrieved via evil alignment prompt. The second uses ideators automated generation to create diverse adversarial document samples specifically for RAG scenarios. The third is that layout-based prompt injections, where I exploit how VLMs parse document structures to embed invisible instructions. Third, the defense mechanism defense mechanism design is the core defense I am developing is hidden detect RAG, adapting the hidden state monitoring approach specifically for RAG generation. The key difference is that I'll monitor activations not just during input processing but throughout the generation phase where retrieved documents are in context. So I will also implement cross-modal consistency checking, comparing OCR extracting text against the VLM visual interpretation to detect discrepancies that might indicate visual prompt injection, and attention-based filtering to identify suspicious visual patterns in retrieval documents. Fourth, and comprehensive evaluation across different domains, medical, financial, and scientific documents to measure attack success versus defense effectiveness, and critically analyze the privacy, utility, security trade-offs. So this framework provides both offensive and defensive perspectives, which is essential for building truly robust systems. So let me get more specific about the attack implementation. Um, uh, so I I'm building on three published attack methods, but adapting LAM for the REG context. So attack one, MML inspired visual document poisoning. The original MML paper attacked standalone VLMs on adapting their encryption decryption strategy for RAG. Here's how it works. I will take harmful instruction and encrypt them through image transformations, maybe like subtle layout changes, embedded text, or pixel level modifications. Then I would inject these documents into ColPali's knowledge base. The key question is, can I craft these documents so that specific evil alignment text prompts cause ColPali to retrieve them with a high probability? If successful, when the generate generator VLM processes the retrieved encrypted document along with the decryption prompt, it should execute the hidden harmful instruction. Given that MML achieved almost 98% success on standalone GPT-4o, I expect high retrieval success, but the interesting question is whether the retrieval stage provides any implicit filtering. Okay, so attack 2, ideator based automated jailbreak generation. Ideator use a VLM plus diffusion model to automatically generate diverse multimodal jailbreak samples. I will leverage their VL break bench dataset, like 3.6 thousand trans pre-generated samples and test their transferability to ColPali-based RAG systems. The original paper showed like 20, not 20, 82 to 88% transfer rate between different VLNs. Well, these attacks transfer to RAG systems, so the test whether the retrieval mechanism provides any robustness. Okay, the third attack is cross-modal prompt injection using uh, what is steganography? Is this correct? Steganography. Okay, sorry. So using the cross-modal prompt injection using steganographic embedding and visual structure manipulation. So this is inspired by the medical VRN attack from Classmam. I will hide some instructions, maybe in document layouts, maybe in margins, headers, or even watermarks, or using subtle typo, typography that are invisible or innocuous to human but detected by VLMs. So the target application are healthcare RAG for radiology reports and financial documents analysis, where such manipulations might seem like legitimate formatting. Okay, the novel contribution here is clear. This is the first, maybe. I haven't scrutinized all the state of the art related works, or will do it in this week. Uh, I may be the first systematic adaptation of state of the art VR and jailbreak attacks specifically to the RAG context. So, um, nobody or a few has tested whether retrieval provides implicit defense or how attacks need to be modified for the two-stage retrieval generation pipeline. Okay, so now let's get into the concrete implementation details, starting with the RG's attack stack I'll be building. So for visual retrieval, um, I will use ColPali version 1.2, specifically the model checkpoint video ColPali v 1.2 from Hugging Face. This is based on the Polygamma VLM and uses a late interaction mechanism similar to Cobert. Instead of creating a single embedding per document, it maintains multiple embeddings, allowing fine-grained matching between query and document patches. To simplify integration, I'll using ByLD, which is a Python wrapper around ColPali. It handles the messy parts, covering PDFs, converting PDFs to images, managing embeddings, interfacing with the vector databases. The the tagline is RAG. I believe it is Otali mini sister project. I believe that is how it is called, making it easy to use with a familiar API. For the vector database, I am using Qdront because it has native support for multi-vector storage, which is essential for ColPali late interaction approach. So standalone vector databases assume one embedding per document, but ColPali needs to store and query multiple embeddings per page. For generated VLMs, I need diversity to test attack transferability. On the commercial side, I will test GPT-4v from OpenAI, Cloud for, I'm not sure it's 4 or 5, or maybe it's a 3.5, right? The latest like 4 point whatever. Yeah, Sonnet from Anthropic, and Gemini 1.5 Flash from Google DeepMind. These represent different architectural approaches and safety training methods. So on the open source side, I will use LL Lava 1.67b, Mini GPT-4, and Instruct blib. The selection criteria is to cover different vision encoded architectures, different language model backbones, and different training procedures. So all the code is open source, I believe. Hope so. The ColPali repository is at this GitHub, right? I will put the link in the Antio core discussion, and Belodi is also has GitHub for reference. So everything I need is publicly available, which is very helpful and very important for the reproducibility. Okay, the slide show the adversarial dataset I will be using. I want to emphasize that all these are publicly available as the models introduced in the previous page, and the dataset are downloadable right now. So I will try to verify each link myself again. First, the VL break bench from the Ideator paper. This contains almost 4,000 multimodal jailbreak samples split into base set and a more challenging challenge set. It's available also in this URL, okay, and they are automatically generated at scale. Second is the MN safety bench from ECCV 2024 paper by Liu, and has around 5,000 text image pairs across 13 different safety scenarios. It's also available on GitHub. The dataset used query relevant images paired with malicious text query, a different attack paradigm from Ideator, so it's valuable for cross dataset validation. A third one is the so-called jailbreak v28k. This is massive, 28,000 jailbreak pairs. It includes 8,000 image-based attacks and 20,000 text-based ARM attacks that transfer to multimodal settings. It's on Hugging Face, and for my project, I will use a subset, probably the 28,000 image-based attacks because testing all 28,000 would exceed my timeline. Okay, so my dataset selection strategy is pragmatic. The outbreak bench is the primary dataset for initial experiment. Highest quality, good size, manageable scope. Safety bench provides cross dataset validation to ensure my findings aren't dataset specific. And jailbreak V28 case subset lets me test whether VLM jailbreak attacks transfer to multimodal RAG setting. I want to stress again that all these datasets are publicly available right now and no data collection bottleneck, so I can start experiment immediately right now or this week later after setting up the RAG pipeline. Okay, where are we right now? Okay, so now let's talk about the clean documents that will populate my RAG knowledge base. Um, what's this part? Uh, Let me think. I want to be very realistic here about what's achievable in the given timeline. So options one is archive papers. Maybe I could download 100 to 200 machine learning or AI papers that contains figures, equations, and tables. Exactly the kind of visual-rich content like ColPali excels at. So these are freely accessible via archives, bulk download API or their regular APIs. The use case would be scientific. Hmm? Scientific. I'm not sure which field I will be using, but mm, in the overall arching, that will be scientific document or question answering. So the question is like, can researcher query the RG system about methodologies, results, or equations? Option two is corporate financial documents, specifically 10K annual reports from Fortune 500 companies, which are publicly available from the SEC's EDGAR database. So these contains extensive charts, tables, and financial data visualizations. I would like to collect like 50 to 100 of these. So the use case is financial documents analysis. So can an analyst query about revenue trend, balance sheet, or risk factors, etc. But here's my honest recommendation. Option three: use existing ColPali demonstration documents. The ColPali repository includes sample PDF specifically for testing. This is much faster to set up. Doesn't require corpus curation, and that's me focus on what's truly novel in this project: the attack and defense mechanisms, not document collection. So my pragmatic target is 100 to 200 clean PDFs. This is sufficient to test retrieval attacks and defense mechanism. The goal here isn't to build production scale RAG system, is to demonstrate and analyze security and vulnerability in RG systems. And this is important. My focus is on attack methodology, not on building large scale document collections. The scientific contribution is in understanding how adversarial attacks manifest in multimodal RAG, not in corpus size. Okay, so let me describe the defense implementation, starting with the primary defense mechanism. So hidden detect RAG is my adaptation of the hidden state monitoring approach from Zhang at ACL 2025 paper. The source paper is in archive, and importantly they have released open source code on GitHub. And here's adaptation for RAG. The original hidden detect monitors hidden states only detects hidden state only during the input processing. So when the VLM receives a prompt, it checks for distinct activation patterns that indicate unsafe content, but in RAG, the threat comes from retrieved documents that are added to the context. So I need to monitor the hidden states during generation, not just input processing. So specifically, when ColPali retrieves the visual documents and they are fed to the generator VLM, I will monitor the model's internal activation to detect if these retrieved documents are triggering unsafe patterns. The key advantage is that this is tuning free, no retraining required, so it's immediately deployable. For baseline comparison, I'm implementing three standalone defenses: input sanitization using perceptual hashing, and adversarial pattern detection on images before they enter the RG system, and output filtering using Llama Guard, which is Meta's harmfulness classification model. It analyzes generated tags and flags potentially harmful context, and prompt-based defenses where I add safety instructions to the system prompt, similar to what Safety Benchmark recommends. The novel defense components I am proposing here is cross-modal consistency checking. Here's the idea. I extract text from the document using traditional OCR, and separately I ask the VLM to describe what it sees in the document. And then I compare these two interpretations. High discrepancy might indicate visual prompt injection. The OCR sees innocuous text, but the VLN is picking up hidden visual instructions. So this defense stack gives me strong baselines for comparisons and a novel RAG specific approach for evaluation. So okay, this might be the last. Now let's discuss the experimental design and how I will measure success. So I'm organizing experiments around four research questions. The first one is how effective are visual poisoning attacks on ColPali retrieval, and the test whether injecting a adversarial document into the knowledge base allow attackers to manipulate which document get retrieved for target query. And the second research question is, can adversarial images inject prompts that VLN generators execute? This test the end-to-end attack. Does retrieval plus generation results in harmful output? The third question is, what is the membership inference risk in visual RAG? Can an attacker determine if a specific document exists in the knowledge base just by querying the system? The fourth one is, can defenses detect attacks without degrading retrieval quality? So this is the critical question. What's the privacy utility security trade-off? So for evaluation, I am using comprehensive metrics across four dimensions. Attack success is measured by retrieval ASR. What percentage of queries successfully retrieve poisoned document, injection success rate for prompt in execution, and MIA AUC for membership inference accuracy. And retrieval quality on clean document is measured by NDCG at K and recall at K, which are standard information retrieval metrics. I need to ensure defenses don't hurt legitimate retrieval. So generation quality is measured by exact match and F1 score. Okay, it's quite standard for answer accuracy plus a harmfulness score for safety. So defense effectiveness is measured by detection rate, what percentage of attacks are caught, false positive rate, how many benign documents are incorrectly flagged, and latency overhead. Is the defense fast enough for production use? Okay, so I'm comparing against three baseline: vanilla ColPali RAG with no defense, the establish the attack surface, and input sanitization, test whether filtering malicious images before indexing helps, and output validation test whether filtering generated text catches harmful outputs. The experimental design provides comprehensive evaluation across attack's effectiveness, defense capability, and practical deployment. Uh, Finally, let me share my hypothesis for what I expect to find based on the prior literature and the unique properties of RAG systems. So for MML inspired poisoning, the original MML paper achieved like 98% attack success rate on standalone GPT-4o. However, RAG introduces an additional retrieval stage. My hypothesis is like maybe 80 to 90 retrieval success. Why slightly lower? Because the retrieval stage might provide some implicit filtering. So ColPali's similarity matching might naturally rank adversarial documents lower than generally relevant clean documents. But I expect the decryption approach will still be highly effective. For ideator generated jailbreaks, the original paper showed 82 to 88% transferability between VLMs. My hypothesis is still lower, if from 70, around 70 ASR when transferred to RG systems. The retrieval stage again might provide some filtering, but given the diversity and quality of ideated samples, I expect high transfer rate. For steganographic, sorry. So for uh, for the steganographic injection, I'm more conservative, like 40 or 50, even 50% success. So these attacks rely on subtle visual patterns that might not survive the retrieval process, especially if ColPali focuses on semantic context rather than fine-grained visual details. So for defenses, let's see. Uh, Defenses. I expand the hidden detector RAG to achieve like 17.5 detection rate. The original hidden detect surpassed state of the art on standalone VLMs, but adapting it to RAG introduces new challenges like monitoring activation during generation is more complex than during input processing. So cross-modal consistency checking, my novel component, I expect like 60, 70 detection with less than 10% false positive rate. It should catch visual prompt injections that create discrepancies between the OCR and the VR and the interpretation. The combined approach using both hidden detect rate RAG and cross-modal consistency, I expect 85 or higher detection rate with 5 to 10 utility loss from false positive or additional latency. The really important contribution will be the insight. The first, quantifying attack transferability from the standalone VLNs to RAG systems. Does the retrieval stage provide implicit defense? By how much? And second is evaluating if a retrieval provides implicit filtering. If ColPali naturally rank adversarial document lower, we might be able to design better defense by exploiting this property. Third, determine optimal defense point in the RAG pipeline. Should we filter before retrieval or after retrieval or during generation? What's the trade-off? So these insights will directly inform how to build secure multimodal RAG systems for production. So let me walk you through the project timeline and key milestone leading to December 10th presentation. Week 1 to from October 22 through November 5th includes today's proposal presentation. My task is our setup and data preparation. I'll install ColPali by BLD and all the VLM dependencies are download and preprocess the three adversarial dataset V Bridge Bank, ML Safety Bench, and Jailbreak V28K subset. And critically, I'll establish a baseline RAG pipeline and verify it works end to end with clean documents. Week through 3 and 4, November 6 to November 19, attack implementation. I will code the visual corpus poisoning attack inspired by AML. I'll implement prompt injection via image manipulation using this steganographic techniques, and I will run initial experiments on a small dataset to debug maybe like the attack codes or understand baseline attack success rate. Week 5 and 6, November 20 through December 3rd, defense design and full experiment. I will try to implement the hidden detected RAG adaptation with activation on the train during generation. I'll code the cross-modal consistency checker comparing OCR versus VLM interpretations, and critically, I will run comprehensive evaluation across all attack types, all defense configuration, and all model combination. This is the most intensive experiment period. So week 7, December 4th through December 9th, analysis and presentation preparation. I'll perform statistical analysis of the results, including significance testing. I'll create a visualization, attack success rate plot, defense performance comparison charts, trade-off curves, etc. And I'll prepare the final presentation slide with results integrated. And on December 10th, final presentation, right here in class. So after December 10th, I will write the 6-page ICML format final report, incorporating my feedback from the presentation. I have built in contingency plans, and if time is limited, I'll focus on attacks 1 and 2 and skip the membership inference components. I'm using pre-trained models only, no fine-tuning to save time, and I can leverage the safe RAG benchmark infrastructure if it's properly available to speed up evaluation. Though the timeline is realistic and accounts for potential delays, I'm confident I can deliver a complete project by December 10th. And that's it. For key reference, I think most of the papers were introduced or reported by by Professor Chen or a student, so I'll skip this part. Okay. Yeah. Thank you for listening. If you have any question, just leave a message down in the YouTube video. Thank you.